Dear students, welcome you again for the second semester BSc Physics class. In this session, we shall discuss about longitudinal vibrations in a rod. So far, in the previous sessions, we have discussed about the velocity of a longitudinal wave or a sound wave in air medium. In a similar way, in this session, we will discuss about the velocity of the longitudinal vibrations in a rod. Let us consider a thin solid metallic rod which is placed in such a way that the axis of the rod coincides with the x-axis. Let A be the cross-sectional area of the rod. Here in the picture you can observe the rod is placed along the x-axis, and we can consider two vertical planes which are perpendicular to the x-axis along the length of the rod. The planes are A and B. So these two planes are having area of cross section A, which are at a distance x from the origin. The plane A is at a distance x from the origin, and the plane B is at a distance x plus delta x from the origin, respectively. These positions A and B are before the longitudinal wave passes through the rod. After the longitudinal wave passing through the rod, the positions of the sections A and B will be shifted to A dash and B dash, respectively. Now let a longitudinal wave propagates along x-axis in the rod at a particular time t. As we said, now the plane A displaces to the position A dash, and the plane B displaces to position B dash, such that the displacement of plane A is y and the displacement of plane B is y plus dy by dx into delta x. Now, as the vertical planes displaces, there will be increase in length of the element of the rod. The increase in length of the element AB of the rod can be given by y plus dy by dx into delta x minus y, that is equal to dy by dx into delta x. Therefore, we can say that there is a longitudinal strain took place due to the propagation of the sound wave in the rod. This longitudinal strain is the ratio of change in length to the original length, that can be given by dy by dx into delta x divided by delta x, that is equal to dy by dx. The increase in length of the element of the rod will set up the internal restoring force within the body of the material, which tend to bring it back to the original length. There will be a restoring force developed inside the rod. Now, if y is the Young's modulus of elasticity of the material of the rod, then we can write the Young's modulus is equal to longitudinal stress by longitudinal strain, that is equal to F by A divided by dy by dx, where F by A is the force per area which is considered as longitudinal stress, and the longitudinal strain will be dy by dx. Now the restoring force F acting per unit area on the layer A dash is given by F is equal to y into A into dy by dx. This is equation number 2. The force acting on the section B, now which is displaced to B dash, is given by F plus df by dx into delta x. So where this df by dx is the rate of change of force with distance. Hence the resulting force acting on the element is equal to F plus df by dx into delta x minus F, which is equal to df by dx into delta x. Substituting the value of F from equation 2, we get F is equal to d by dx of y into A into dy by dx into delta x. That implies F is equal to y into delta x into A into d square y by dx square. If d square y by dt square is the acceleration alpha produced in the element by the force in the direction of the velocity, then the force acting on the element is, according to Newton's second law of motion, F is equal to m into alpha. Here m represents the mass of the element, which is a product of density and volume enclosed between the two elements, and we have represented alpha as the acceleration. Instead of A, we have denoted as alpha as the acceleration, since we have taken the area of cross section as A. In order to reduce the confusion, acceleration is denoted as alpha. According to this equation, we can write F is equal to rho into delta x into A into d square y by dt square, where rho is the density of the material of the rod. Now from equation 3 and 4, comparing these two equations, we can write rho into delta x into A into d square y by dt square, that is equal to y into delta x into A into d square y by dx square. This in turn can be written as d square y by dt square, that is equal to y by rho into d square y by dx square. Now we know that the general differential equation of wave motion can be written as d square y by dt square is equal to v square into d square y by dx square. Comparing the equations 5 and 6, we can get the equation as v square is equal to y by rho, which is the equation of the velocity of the longitudinal wave in a rod, that is given by v is equal to square root of y by rho. So hence we have discussed about the vibration in a rod. The vibration can be set up by different means in the rod, and the vibration propagates along the length of the rod along x-axis, and this vibration set up the increase in element of the rod, and the vibrations will be moving with the velocity v is equal to square root of y by rho. So this velocity of the vibrations set up in the rod is directly proportional to square root of the Young's modulus of elasticity of the rod, and it is inversely proportional to square root of the density of the material of the rod.